we're going to look at one of the classic experiments that proved the photon model of light. This is called the photoelectric effect, and it's based on this apparatus. Basically, we have a pair of electrodes in a evacuated glass tube, and we've got a adjustable voltage supply, so we can change the voltage between these two electrodes, and then we can measure the current in some way. Now, obviously, to begin with, you're not going to have, no matter what voltage we do here, we're not really going to have any current because there's a break in the circuit. So, but what the photoelectric effect does is that when light falls onto one of the electrodes, and this is set up the negative electrode, as shown here, electrons absorb energy from the light and are liberated from the metal, and then they flow from one electrode to the other, producing a current that you can measure. What you can do is reverse the polarity of those electrodes so that the electrons are coming off the positive electrode and heading towards the negative electrode. So obviously that's going to start to slow them down, and if they don't have enough kinetic energy to overcome that potential and get all the way to the negative electrode, which is trying to repel them, they will turn around and fall back. So what you can do is, when it's in this negative setup like this, you can adjust that voltage, increase it slowly from 0 with the light falling on the electrode until the current just disappears. And when the current just disappears, you know that even the most energetic electrons are not quite making it to the other side, and so you can use that to measure the kinetic energy that electrons are leaving that surface. The potential that it does that is called the stopping potential. So classical physicists, or physicists at the time this experiment was first done, thought of light as an electromagnetic wave, and they thought in terms of a classical idea of a wave. And if you think of light like that, then there should be 3 predictions you could make about what should happen here. The first is that the kinetic energy of the electrons will depend on and be proportional to the amplitude of the light. So in classical physics, the amplitude of a wave is what gives you the energy content of the wave. And so classical physicists felt that the electrons should absorb that light energy until they had enough energy to leave the metal and cross the gap. The intensity of the light, so the brightness of the light, which gives you the amplitude of the wave, would determine how much kinetic energy they got. The second prediction is that the effect should be more or less frequency independent. The frequency of a classical wave does not really determine its energy content. It's the amplitude that's important. And then the final thing is that there should be a time lag between irradiation and emission. The electron sitting in the metal has to absorb energy from the wave until it's absorbed sufficient to break free and move. So the process of absorption is one that takes a certain amount of time, and it depends on the amplitude of the wave and depends on the kind of losses of energy within the metal, etc., etc. So there should be some sort of time lag between the light turning on and the emission starting. So, doing this experiment, do the experiment. So the first thing that happens is that the emission is actually completely instantaneous with turning on the light. There is no time lag at all. So that prediction is completely killed off. When you look at the current versus frequency graph, so you change the frequency of the light, the current does not seem to be affected at all. However, the kinetic energy of the electrons that are produced is strongly dependent on the frequency, which is exactly the opposite of what was predicted. So as the frequency goes up, the electron kinetic energy goes up, but it doesn't go through the 0. there's a cutoff frequency below which you get no emission whatsoever. So remember, low frequency means high wavelength. So long wavelength light produces no electrons at all, and so the kinetic energy is zero. Above some cutoff frequency, you do start to get emission, and it's linearly dependent. So that prediction is killed off. Finally, the light intensity does not affect the kinetic energy at all. Very, very unexpected from a classical point of view. As long as the light is above the cutoff frequency, then changing the light intensity will not change the kinetic energy of the photons, of the light. Will not change the kinetic energy of the electrons. The light intensity, though, will affect the current. So as you increase the light intensity, again, as long as you're above the cutoff frequency, you'll get more current out. So none of this makes any sense from a classical point of view. So the photon model is what we need to kind of rescue us from this. So how does the photon model help us? Well, in the photon model of light, each photon is an individual particle, and the absorption of light, rather than being a gradual thing of a series of waves washing into the electron, is a single instantaneous event. The electron absorbs the photon is destroyed, all of the energy of the photon is transferred immediately to the electron with no time delay whatsoever. And that energy depends on the frequency of the photon, the wavelength of the photon, given by Planck's constant times the frequency. So that explains why there is an instantaneous change. It also explains to us why the frequency does not affect the current. A certain number of photons per second will produce a certain number of electrons per second, irrespective of what the energy of those photons is. Whereas the kinetic energy of the electron is clearly the energy of the photon minus any energy that is required to break free from the surface, which is called the work function of the metal, or of the material. So this gives us straight away our little straight line graph with a non-zero intercept. The slope of this graph is obviously going to be Planck's constant, linearly dependent on the frequency, and then our intercept comes from the fact that this work function has to be overcome. So if the photon does not have sufficient energy to overcome this work function, the electron will not have sufficient energy to break free, and so it will not be emitted from the surface. And that doesn't matter how much energy you put on it. So the light intensity is not going to affect the electron kinetic energy, because in the photon model, the light intensity is just number of photons per second. It's not to do with the amplitude of waves, and so as you increase the light intensity, you'll get more photons, but more electrons, but they will all still have the same kinetic energy. The fact that you get more electrons, though, does mean that the current will go up as you increase the light intensity. So these graphs are all very nicely explained by the photon model rather than the wave model. So to summarize, in the photon model, if the photon has enough energy to overcome the work function, it can produce one photoelectron. So photoelectron is just an electron that's being produced in this manner. It's not a special flavor of electron. So in this case, we've got blue light falling on our electrode. We're going to get electrons coming off. If we switch to red light, those photons do not, in this case, have sufficient energy to overcome the work function, and so you get no emission whatsoever. And it doesn't matter how bright you make the light source, each individual photon interaction is not sufficient to produce an electron, and so you do not get photoemission from the surface. So the photon model really explained the photoelectric effect. It was Einstein who actually suggested the photon model for the photoelectric effect, and together with black body radiation, which we'll talk about in a later video, really sealed the idea that light was consisted of photons. So right away there is like an application for this technology, and one of the first optoelectronic components that was ever created was based on this method, and it's called the photomultiplier tube. You can still get them now. The first television cameras were actually made using this technology. They're still used a lot in all kinds of particularly scientific applications. So, for instance, the Sudbury Neutrino Observatory in Canada is basically a huge ball filled with water, surrounded by photomultiplier tubes. Neutrinos come through; they hit molecules inside the ball, produce photons, and the photomultipliers are able to detect those photons. So, how does it work? Basically, a photomultiplier tube, a photon will come in from one end, from its sort of active end, where there's like a thin foil or a thin coating of the metal. That is at a high negative voltage. Then throughout the body of the photomultiplier, there's a series of electrodes, each one at a slightly less negative voltage. So between any two, there is an electric field that will accelerate electrons between them. The voltage is usually high; it can be kilovolts. So a photon comes in, creates a photoelectron. That photoelectron is accelerated by the potential difference to the first electrode. They're called dinodes. That acceleration means this photoelectron, when it reaches here, has more energy. It has enough energy to knock maybe 2, maybe 3 more electrons off the surface of this dynode. Those secondary electrons, as they're called, are accelerated to the next dynode, where they knock 2 or 3 off each. They're accelerated to the next dynode, and the next, and the next, and the next, and you go through a series of stages, each one producing, doubling, tripling, quadrupling the number of electrons, until finally at this anode you have a huge avalanche of electrodes. Those electrons can flow through the resistor here to ground and can produce a voltage pulse out of the whole thing. And that voltage pulse can come from a single photon. You can produce a measurable current, measurable voltage out of this device from a single photon if the thing is set up right. So they are extremely sensitive devices that can measure extremely low light levels. And so they're frequently used in situations where you're expecting just a photon or a very, very dim burst of light. For instance, in the Neutrino Observatory, but also in lots of biological applications where you're looking for fluorescent emission from very, very small amounts of fluorescent molecules, maybe in a cell. So the photomultiplier is still very widely used, has several advantages. It's very fast, so it responds in nanoseconds to the absorption of the photon. The delay is from the electrons going through each of the stages, but that's still just nanoseconds. They're extremely sensitive, as I said. They can go down to detecting single photons. They require no external amplification generally, because that high voltage stages amplifies the single photoelectron to produce a substantial current. So that means that the following electronics can be very simple. They do have some disadvantages, which means that as optoelectronic components, they are nowadays relegated to very specialist applications. They are very expensive. They can be from a few $100s right up to thousands, tens of thousands of dollars for the very specialized ones. They're physically bulky. They tend to be no less than maybe a few centimeters in size, but they can be up to tens of centimeters in size. They can be very, very big. They can sometimes be too sensitive. So because you get this huge avalanche of electrons, you can actually damage them by putting too much light on. If you put a large flash of light onto a photomultiplier, you get a gigantic avalanche of electrons which can actually burn the thing out. They're also then not very sensitive at longer wavelengths, and that's because they work on the principle of the photoelectric effect. If your photons do not have sufficient energy to overcome the work function of that first photocathode, you'll get nothing out of them at all. And so they tend to have a strong cutoff and are used more in the ultraviolet and the blue end of the spectrum rather than in the visible and the red, though you can get coatings that allow you to do visible light as well. They are sometimes coupled with what are called scintillator crystals to turn them into particle detectors, where some particle like a proton or electron hits the crystal, generates a flash of light, and that can then be detected. So, in summary, one of the first optoelectronic components, a very, very high performance light detector, not terribly useful in a lot of practical situations. So, for instance, you won't be having one in your kit because we can't afford them. Next time we will look a little bit at optoelectronic components that, rather than being based on the photoelectric effect, are based on the absorption of photons within materials, which leads to more compact and lower cost devices. But we'll look at that in the next video. Okay, thank you.